ahead and get this party started. Audio and video is up. We are live. Welcome to Senior Seminar. We are actually, I was looking at the schedule. I'm like, wow, we're in week 9. Like, it's insane. It's weird how time has, it's like it almost goes slow and fast at the same time with how things are going these days. I want to talk about sort of my plans for not just, the FE review, but kind of wrapping this semester up. Because we're running out of weeks, and I want to make sure that the review sessions are valuable, but I don't want this class to be just FE review. I want to cover some other topics. So what we're going to do is we're going to do Geotech review this week, and we're actually going to do some Geotech review next week. The reason why is if you look at the, first off, if you look at the polls, the remaining topics that are of import that everybody said they were really interested in reviewing, and specifically the ones that had a lot of questions, were structures, geotech, and water resources. But first off, I'm not going to be the best at reviewing water anyways, and it's not as big of a section on the exam. And so that left structures and geotech sort of as some culminative review, and there was largely similar interest, but the thing with the structure review is we could still maybe do like a week of structures review, but I'm hesitant to do the steel and the concrete sections because there's some people in here that have only had one of those classes, and there's some people in here that have had neither of those classes. And so I don't really see value in that. I don't want to isolate some folks, but just about everybody in here should have had geotech. So it's a perfect topic to review, and it's a big one on the exam. And there's some stuff on geotech that kind of, fits into other disciplines. For instance, I'm probably not going to do a sieve analysis today, but if you can do a sieve analysis, that helps not only geotech, but it helps civil engineering materials as well. Now, my plan for quizzes is this. I never got around to recording that math review, but I still want to pre-record it, simply because math is, it's the topic, like every topic on the exam has math in it. And so it's just such a seminal skill on the exam. So I do want to do that, and I think I'm going to pre-record it. And hopefully I might try and do that today. And if I pre-record that today, what I'll do is I'll post a quiz on math for this week, and then do the geotech quiz next week, because I want to do geotech again the following week, because there's just too much to cover. Like if you look at the geotech section, there's a lot there. I'm not going to cover all of it, but I'll cover the stuff that I think is critical and the stuff that I think you're going to get, seminal problems on the exam. What we're going to do today is we're going to do about 4 problems in geotech land, and then we'll do maybe 4 or 5 more next week, and I think that'll wrap that up. What I'm hoping to do the following week is to actually get into some stuff outside of FE review. I spoke with Dr. Bryce, and there's a topic that we want to cover in senior seminar, which we may not cover explicitly in a lot of our classes, and that's the idea of sustainability. And it's something that you all need to be aware of. And there's one topic I want to cover with you all, which is some of the professional tools that you need to understand getting out of here. And it might seem, elementary, but simple things like how to use Teams, how to use Office, how to use Outlook, all that stuff. I'm telling you, it's really important when you get out of here. And the better you are at that stuff, the more effective you're going to be as a practicing engineer. So let's jump right into it. Are there any questions, though, about logistics? So you're going to get a math quiz this week and a geotech quiz next week. Any questions before we get rocking and rolling? Was that a pun on geotech? I don't know. Unlike Dr. Na, I'm sure I'm not really saturated with a lot of these geotech puns.
So what's the story on surveying? Because we have to watch the video and then do the quiz later, correct?
Was there not a quiz? Did that quiz not post?
I don't know.
Hold on.
Yeah, I see it now. I must have missed it because with all the video recording, then the I'm sorry, I must have. I'm a little confused.
Did everybody else get it? Hold on. I don't want to. If I made a mistake, I'll extend some time on it. me check something. We got actually you took that quiz.
Oh, I'm sorry. I'm confused. It must be related to the
math quiz. That's the one I didn't post, and
yeah.
that was on me.
Sorry, I got a little.
Now I'm not sure if I posted the solution yet to the surveying quiz, but I will.
Okay.
I'll check that after this. All right, let's jump into geotech land. I've got 4 problems. I was gonna do 5, but I'm worried about time. Let me walk through the problems with you, and then we'll get into it. So the first problem, this problem here is I would say key in terms of like you will get a problem like this. Very, very high chance that you will. This is a soil phase or an index property, whatever, air, water, and solids problem. Here's a sample, here's some properties, compute some other properties. Like this is a very typical problem on the exam. The second problem is a classification problem. This is a soil classification problem. Again, very typical. You would very high chance that you would get a problem like this on the exam. The third problem is a flow net. I'm assuming you all have done flow net problems. Am I correct? I would say that everybody in here has experienced with a flow net problem. This problem 3, it's the same problem. Like this is a tiny version of the flow net, and this is a bigger one blown up. And then effective stress. I think those are 4 problems that I think are pretty representative of soils land. And then I think what we'll try and do next time is to look at maybe consolidation, maybe some bearing capacity next week, to try and tie up the big picture. Everybody good? All right, let me stop the quiz, or stop the quiz, stop the share. Give me a sec. Sharing up. There we go. Okay. All right, so let's jump right into it. We're going to start off with this soil phase diagram. I don't know if maybe Dr. Knott called them index properties or soil phase properties. It's all the same stuff. I'm trying to get a little bit more organized here. Okay, so in this problem, what we've got is an undisturbed sample of clay. It has a wet weight, a dry weight, a total volume. We've got the solids have a specific gravity, and what we're trying to find is the void ratio. This is sort of the way that I learned it. I'm not sure how you learned it. Let me make sure my pen's up. This is how I always learned how to do it. So the first thing I would do is I would draw myself a little column of soil. Actually, let me lower that a bit. And so let's say this is my soil sample. The soil sample has 3 quantities. It has air, it has water, and it has solid. Okay. And what I would then do is I would say, okay, let's maybe pick the right side and put all the volumes. And over here, let's put all the weights. And you could do this in terms of weights. You could do it in terms of mass. Everything we were given here was in terms of weight. So I think that's the easiest way to go about it. So over here on the left, let's start with the left first. Okay, so here's this, here's this, here's this, here's this. So let's start filling in some things that we know. Maybe I can just extend that out. Let's start filling in some things that we know. So this problem told us that we have an undisturbed sample of clay, and it has a wet weight of 220 pounds and a dry weight of 205 pounds. So help me out in the chat. the wet weight. Which is that? Do we know what that is? Is it, you know, the weight of the water, the weight of the solids? Like, what is the wet weight? And then, in turn, what is the dry weight? The total weight is the wet weight. That's exactly right. So we'll call this WT is 220 pounds. Exactly right. And then the dry weight is the weight of what? The solids. There we go. So this is the weight of the solids, and this is 205 pounds. So right off the bat, can we determine the weight of the water in the air? Well, first off, what is the weight of the air? At 0. There you go. The air has no weight. It doesn't mean it doesn't have volume. That's a different story. But that doesn't mean it doesn't have volume. But it doesn't have a weight. So what's the weight of the water? I mean, if the weight, the total weight's 220, so we've got a sample. Yeah, it's pretty 15 pounds. You know, we take a sample, we put it in the oven, we evaporate the water, and it reduces by 15 pounds. That was how much water was in it. Okay, now let's see what we can do over here with the volumes. Now, one of the things we do know right off the bat is we do know the total volume. Okay. The total volume was given to us, that's VT, and that's 1.73 cubic feet. Now, we don't know the volumes of each of the individual components. Like, we don't know volume air, we don't know volume of the water, and we don't know the volume of the solids. But that doesn't mean we can't figure them out, okay? So, for example, let's take the volume of the water, okay? We're using a pretty fundamental relationship. The weight is gamma times the volume, right? Or weight is the specific gravity times the gamma of water times the volume. We can write it that way as well, right? Either one works. So therefore, I could determine the volume of the water by taking the weight of the water divided by the gamma. But keep in mind, I guess technically I would write it like this. But remember, specific gravity water is just 1. Just 1 times that. Okay. So the weight of the water was 15 pounds. And then the unit weight of water, y'all better know that number. That number should be burned into the back of your memory by now. What is the unit weight of water in American units? There we go. 62.4 pounds per cubic foot. This is, when you chug it out, it's 0.24 cubic feet. So the volume of the water is 0.24 cubic feet. All right. What about the volume of the solids? Well, what I'm going to do for the volume of the solids is I'm going to take the weight of the solids divided by the gamma of the solids. The problem is I was never given the gamma of the solids on this problem, but I was given the specific gravity of the solids. So I can say the weight of the solids divided by the specific gravity times the gamma of H2O. So that is 205 pounds divided by, what is that, 2.65? And when you chug that out, 205 divided by 2.65 times 62.4, you get like 1.240 cubic feet. So the volume of the solids is 1.240. So that should be pretty simple. So what about the volume of the air? How do I determine the volume of the air? Well, this is just a dimensions problem at this point. That's one of the reasons why we draw it in this sort of columnar format with the air, water, and solids split up like this. Because if I know that this dimension is 1.73, and I know this dimension and this dimension, I mean, it's pretty simple at that point. I can just, take the difference to determine VA. So VA is VT minus VW plus VS, summation. And so VA, when you chug that out, it ends up being something like 0.25. All right. Okay. Any questions so far? Now, keep in mind, though, whenever you're doing these problems, the goal on this problem is to determine the void ratio. Does anybody remember the formula for the void ratio? And what if you don't remember the formula? What do you do? Remember, you do have this FE reference handbook. Remember that? The volume of the voids divided by the volume of the solids. And it's right here. If I go into the civil engineering section of the reference handbook, it's literally the first section. And what is the volume of the voids? It's the volume of the air plus the volume of the water. Oh, man, I didn't mean to do that. It's the volume of the air plus the volume of the water. So therefore, the void ratio, volume of the voids over the volume of the solids, is the volume of the air plus the volume of the water over the volume of the solids. So 0.25 plus 0.24 over 1.24. When you chug that out, 0.40. All right, are there any questions on that? I mean, hopefully that's like shaking the rust off, if you will, on the on geotech stuff. Let me move this down a bit so that I can sort of scroll this up here and give you all a second to see if you're wanting to copy this down. Any questions? Oh, sorry. I keep scrolling. I don't know what's going on. My tablet's being very sensitive today. Okay, let's get into problem 2. Okay, so problem 2. This is another problem. Maybe not using this system, but the concept of classifying a soil. This is very typical of something that you would get on the exam. You're given a soil with a set of properties and then determine its classification. Very common exam. So an inorganic soil has the following characteristics. We have 69% fines. We have a liquid limit of 72 and a plastic limit of 48. Using the USCS system, Unified Soil Classification System, what is the soils classification? So in order to do this, you really need the reference handbook. So let me go to the handbook a bit. So here's the cover. Here's the beginning of the handbook. And when you go through the sections, the bookmarks, we've got the section on math, section on statics, section on whatever. If I go to civil engineering, the first section within civil engineering is geotech, which, by the way, it is just generally a good idea to look through this because there's a lot of really good stuff in here. You've got soil phase relationships, again, some other index properties of soils. We've got consolidation here and settlement. We've got time factors for consolidation. We got more Coulomb failure criterion, horizontal and vertical stress profiles. We've got Ka and Kp for you retaining wall folks. We've got ultimate bearing capacity. sliding, slip failures. This is AASHTO soil classification, USS soil classification. So we're going to be using this during this problem. If you go into my world in structures land, we have influence lines. We've got truss deflection by the unit load method. The same thing that we've been, for those of you that are in structural analysis, we just got done with that in there. Frame deflection, beams and frames, the unit load method, again, same thing. Some stuff in structures that we're going to be talking about later. And then for those of you that have had steel and concrete, you probably recognize some of this stuff. But let me get back to soils land. For those of you that are in some of these classes right now, structures, geotechnical, it's worth taking a look at this, going through it. There's a lot of really good data here. What I did here on the notebook is I screen capped this page and I put it here so it's a little bigger so that we can kind of read what's going on. Oh, goodness. So let me actually make this even bigger. Okay. So we've got to classify this soil. Okay, so let's see if we can go through this chart and see what we can figure out. So if you remember from soils, you basically start at the left and work your way over to the right to get your classification. So first off, starting at the left, are we going to say that this is a coarse-grained soil, a fine-grained soil, or a highly organic soil? Well, I can tell you we're not going to say it's highly organic because it literally says it's inorganic right here. So is it coarse-grained or is it fine-grained? Let's look at coarse-grained. What are the requirements? It says more than 50% retained on the number 200 sieve. Well, remember remember the number 200 sieve, that anything that passes the number 200 sieve, those are percent fines. This is going to be a fine-grained soil because 69% of the soil is fine, right? So it's not going to be a coarse-grained soil. We're not dealing with a sand. We're dealing with something that's pretty silty, really, really tiny particles. So we're definitely going to be going along this line, okay? So then we go to the next column, and so we have to ask ourselves, which set of rows do we go through? And the question becomes whether or not we're looking at the liquid limit. So the liquid limit less than 50, we go to the upper set. Greater than 50, we go to the lower set. And the liquid limit here is 72. So with a liquid limit of 72, we're going to go here. And we have the question of whether or not it's inorganic or organic. We already said it was inorganic. And then basically we're stuck with these two choices right here, the fat clay or the elastic silt. And the difference between which one we use is a function of whether or not the PI plots above or below the A line on this chart here. So we need the PI. The PI is the plasticity index. Anybody remember how to compute the plasticity index? How do we compute the plasticity index? Anybody remember that from soils? If you don't remember it, you've got the reference manual. And by the way, everybody in here created an NCEES account. You can download the reference handbook from your NCEES account. Anybody remember this? Let's see. Remember that right there? The plasticity index is the liquid limit minus the plastic limit. So, hold on. Yeah. Liquid limit minus the plastic limit. So, 72 minus 48. So 72 minus 48, what is that? 24, right? 24. So I go down here. The liquid limit was 72. So it's going to be like right here. 24, maybe. Maybe right there. And so that plus, this is the A line, so we're well below the A line. So if we're below the A line, we are dealing with an elastic silt. And so our ASTM classification would be MH. C would be our answer. Help me out. I'm not getting a whole lot of response from chat. Any questions on this? Like, is this familiar?
I'm a little bit familiar. By the way, a quick question.
Yes.
I recall that earlier we had I think what was it? I think like statics or geomax, something like that. Well, I think it was surveying. We could eliminate possibilities based on the values given, correct?
That's a great point. Maybe we ought to look at that. That's a really good point. I don't want to interrupt your question.
But as I see here, we're given characteristics. So in theory, we could eliminate some of our possible soil types here.
Exactly right. Like, for example, let's take a look at GW. Okay, GW is a well-graded gravel. Okay, and a well-graded gravel, you're going to be dealing with large aggregate, rocks literally, and that's definitely a coarse grained soil. And when you take just a look at the percentage of fines, I mean, a soil that has, think about the size of the number 200 sieve, right? I mean, it's almost like a fabric that you're pushing the soil through. And so it's certainly not that. It's certainly not that. Now, if we go to ML, ML, that's a possibility. MH is a possibility. CH is a possibility. But like you said, can you eliminate one right off the bat? I think you can eliminate GW right off the bat, just based off of this. Just based right off of that. That's a really good point. I'm glad you're saying that. Now, likewise, if we're talking about test taking strategy, if we look at problem one, I'd say what's one of the answers before you do any math that you can eliminate on problem one before you do any math? I mean, kind of easy to say that now that we've done all the math, but
I say D because the odds are it being 1 seems unlikely.
You're exactly right, but it's not even just odds. It's just the certainty. So remember what the void ratio is. The void ratio is the ratio of the volume of voids to the volume of solids. So I mean, one would say that you've got just as much volume of air and water as you do solids, and that almost doesn't really pass the smell test when you just look at the numbers. Like when you have a wet weight of 220 and a dry weight of 205, I mean, you didn't cook away 100 pounds of water. You only cooked away 15 pounds of water. So the idea that it would be one, I guess not impossible, but it just seems to be a stretch, given the numbers. These are really good points. Really good points. Any questions on this stuff? Because I don't want to rush through this. The idea is, I know we're limited on time, but I would rather take the time and do it right. Let me get a little. I want to make sure I got room on these. Any questions? Okay. If there was one thing in undergrad that I was always really bad at, it was drawing flow nets. Like, I knew what it was supposed to look like. I knew what the answer should have been, but getting my hand to come up with something this pretty, it just didn't happen. They always were ugly. It was like my answer was right, but oh God, it just looked really bad. So I assume you've all done flow nets in geotech. What we've got here is an impermeable dam. We'll say it's like a I don't know, like a rock dam, concrete dam, or something, something like that. We have an impermeable dam, and what is most nearly the total flow of water under the dam per foot of dam width. And the first thing that I guess we should do is make sure that we remember the base equation for flow nets for determining that flow under the dam. And so it equals your coefficient of permeability, right? Which we're given that right here, and we've got the coefficient of permeability. That's easy. We need your change in elevation, your elevation head, which is pretty easy just from the figure. And then we need the term NF over NB, okay? And so NF is the number of equal potential flow paths, and then NB is your number of drops, right? So remember how you draw a flow net, and like I said, I'm going to demonstrate how bad I am at this now. So let's say you've got, some, dam, right? And so here's the elevation of the water before, here's the elevation of the water after. So that right there, that's your delta H, right? And so this is the base of your channel, right? And so what you do is you split the path under the dam into a number of equal potential flow paths. So let's say we do 3. That would be 2 lines, right? And then you draw your lines so that they're parallel, but that they intersect the pass on the other end at 90 degrees. So maybe this one goes, like that, and then maybe this one goes like that. And then the next step is to cut that up with the flow paths into those equal potential squares. Again, I've always been really bad at drawing this. I'm almost kind of embarrassing myself just drafting this out. But that's kind of the idea, and the idea is to determine the number of drops versus the number of flow paths. So if you look at our flow net here, this is it drawn far better than anything I could draw myself. We've got the K value, which is 100th of a foot per minute. We've got the delta H, which is just the total change in elevation. That's 20 feet. What we need are the NF and the NB. So looking at this flow net, help me out. How many flow channels do we have? And the easiest way to determine that is to look right here. Where the under that little sliver of I guess a sheet pile wall behind that dam. Will we have to draw the flow net, or will it be given to us on the FE? You won't have to draw it. I think that's a fair certainty. You'll have to interpret it, and with some of the alternative question types, you might have to point to particular regions on the flow net, but you shouldn't have to draw it. That's why I'm more interested in your ability to interpret it than draw it. So how many flow paths do we have? What's our NF going to be? And how many flow channels do we have right here? Four, exactly right. Because we've got 1, 2, 3, 4. Exactly right. Now, how many drops do we have? I'm calling it MB. I should just call it MD for drops. I don't know why I have MB on my notes. It's ND. Number of drops. How many drops do I have? Ten. Exactly right. So the idea is that this is where you start, right? Because the idea is to determine the change, the drop in energy through the porous media. So that's where you start. And so I've got 1, right here. So that's a drop. 2, 3, 4, 5, 6, 7, 8, 9, and then we consider that our end. And so the idea is that's the end. So between those, we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 drops. So therefore, our Q, let me scroll down here. So Q is K times your delta H times your number of equidistant flow paths divided by the number of drops. So 0.01 feet per minute. And then 20 feet. 4 over 10. Now, if you look at the units are going to be feet squared per minute. And you're like, wait a minute, all the units in the answer are cubic feet per minute. So where's that extra, where's the other feet come from? Remember, this formula tells you the flow per foot of dam. Remember, the dam extends in and out of the screen forever. And so we're just looking at the flow per foot of dams. That's where that extra foot comes in. And so when you check that out, 0.1 times 20 is 0.2. Times 4 is 0.8, divided by 10 is 0.08 cubic feet of flow per minute. Back to the answer. Oh, I know what's wrong. I have a typo in my question because these are off. I apologize for this. These answers were supposed to be 0.08. 0.16, 0.24, 0.32. I remember that I had originally typed out this question and I had that error and I never fixed it. My apologies. They're supposed to be a one-off. Sorry. But do we generally understand the process? Understand the means of interpreting the flow dam? That's really what I'm after. I'll fix those choices when I upload the slides. I haven't actually uploaded these slides yet because I was going to upload the math slides and then do it all at once. On the FE questions will be like this for flow nets. I mean, I can't tell you every question that they're going to put on the FE, but I can say that this is representative of what you would get on the FE. I mean, you might be given think about this problem, think the different ways that it could be asked. Maybe the question is, okay, what does K need to be such that, you have a particular flow or, what have you. Again, I don't see you drawing flow net exam. I mean, you're literally just there with a mouse and keyboard and whatnot. I had an echo there for a second. Any other questions? This is good stuff. Hold on. Yes.
But on the question for a moment here, it seems to me that some of this has to be very the calculations have to be go through all the calculations promptly because this is a very changing situation. So my question is, what kind of problems should we look at if we can't eliminate variables? Like the answers here.
So for this problem, I'm not sure that you could eliminate choices by just looking at it, and not all problems are going to be like that. And in that instance, just start doing the problem. But I fear I didn't answer your question.
Well, you kind of did, but I'm also curious. But like, in this kind of problem here, for example, at what points can we start looking at our steps here and determining, oh, this can't be this problem, and it can't be this problem? answer meant? Because
I think that's just going to vary from discipline to discipline. Like, here's an example, and I'm going to give you a structures analogy. Truss analysis. Okay, so if you have a truss here, let me answer it like this. I'll sneak in a tiny truss review. Let me move this down. So let's look at a basic problem. Let's take this problem and let's draw a truss up. Let's do this, 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 and let's do members like that, members like that, members like that. And let's put our loads like you would see them in real life on, something like a bridge. Let's put loads like that. And 10 kips, 10 kips, 10 kips, 10 kips, 10 kips. And let's say that the test asked you what's in that member. It's a very common problem that you would get on a structure section. Problem like this. Okay, so let's talk about some test taking strategy. First off, method of joints or method of sections? I'll fill in my little joint symbols here. Because we've got time, and this is a valuable discussion. I can't help but throw in a structures question. So if I was trying to find the force in that member, what would you use? The method of joints or the method of sections?
the joints there. Yeah.
I wouldn't. The method of joints is going to take a long time. I mean, you're going to have to, like, if you let's say everything's symmetric. Okay, so that means this reaction's 25 kips. That means this reaction is 25 kips. This is a fair question. Let's put some dimensions on here, just so that we're speaking the same language. So 6 at, let's just say 15 foot is 90 foot. And let's make this 15 foot as well. So all the members are at like a 1-to-1 slip ratio. All right, let's just game this problem out. Let's do a thought experiment. Okay, so let's say you use method of joints. Okay, so which side do you want to start on, the left side or the right side? Doesn't matter. Let's say the right side. So in order to solve for this member, I have to solve that joint. Then I need to solve that joint. Then it's probably not a bad idea to solve that joint, then that joint, then that joint, then that joint. Now I can probably stop there, because once I get there and I solve, this joint right here, I'm gonna, that's gonna be the joint, and that's the member that I'm after. So I gotta solve 6 joints to get to this member. Whereas with the method of sections, all I gotta do is cut one section and I'm done. Okay, in other words, like my way with the method of sections, all I have to do is cut a section, look to the right, some moments here, and I will get my unknown. Okay, so first thing is to take a second and ask yourself, what's the goal? If this is the goal, what's the quickest way of getting there? That doesn't quite get to Mr. Adkins' point, but there's some discussion to be made about this member. Help me out. Is that member experiencing compression or tension? No math. Just look at the truss and tell me whether or not it's experiencing compression or tension. Compression. Exactly right. That member is experiencing compression. Look, that's a truss. Here's the thing. Trusses, behaviorally, especially trusses like this, are really just beams with really big holes in them. See, let me show you something. Give me one second. See this? Here's a beam, right? When I take this beam and I apply loads downward, it bends like this. The top experiences compression, the bottom experiences tension. This truss is no different, okay? If you go back to the truss, if we go back to the truss for a second, and take just a hard look at it, the top chords of the truss are all going to experience compression. The bottom chords of the truss are all going to experience tension. You can think of the top chords and the bottom chords as sort of being like your flanges in your beam. They're the ones that are going to carry kind of the moment, if you will. The internal diagonals, those are the ones that kind of carry the shear. If you analyze this truss, what you're going to find is that if you look at this diagonal, and this diagonal, the internal forces inside those diagonals are going to decrease as you get closer to midspan. Because if I was going to kind of look at this as if it was one beam, the shear diagram for a beam kind of goes like that. That's not very symmetric. That's a horrible drawing. But you find that the internal forces in those diagonals decrease as you get to the middle, because those diagonals in the middle kind of act like your web, and they kind of carry the shear. So to go back to Mr. Adkins' point, first off, there's strategy. And that's going to change from discipline to discipline. Like, you're going to attack fluids problems differently than you're going to attack structures problems. But the second is just seeing if you can understand behaviorally what's going on. For instance, for those of you who are in structures now, you know, I know that's a zero force member. You know, can you identify any zero force members? Anything you can do to make the problem easier is definitely something that you're going to want to do. We only have like 4 minutes, and I want to really quickly knock out this effective stress problem. So for the soil profile shown, what is most nearly the effective stress at point C? Let me blow this up a bit because that text I know is kind of tiny. So I have, you know, a column of sand, and there's a groundwater table in the middle, and I want to determine the stress right here. And so because that's sand, and because I've got the groundwater table, above the groundwater table, I'm saying that I'm dealing with a dry sand. But below the groundwater table, I'm saying I'm dealing with a saturated sand. So in order to determine the effective stress, remember, the key word is effective stress, not total stress. Does anybody remember how to compute effective stress? You take the total stress, but then what do? You subtract your pore water pressure. Yeah, your mu, or whatever symbol you use. Mu is very, very common. So the way that we would handle this, and it's pretty basic. That's what I say. This problem's really quick. We would say, okay, our effective stress is going to be, gamma dry times 6 meters plus gamma sat times 13 meters, and I'm getting that from here and here, minus gamma H2O, 13 meters. Or, if you want to be a bit lazy, you can say gamma dry times 6 meters plus gamma sat minus gamma H2O, 13 meters. So that's just me doing a little bit of factoring there. So gamma dry is 16.5. Plus, and then a bunch of junk times 13 meters. The gamma sat is 19.25. That just comes, I'm not pulling that number out. That just comes from right there. Minus the unit weight of water. What's the unit weight of water? Last question for you. Mr. Schwartz is dead on. It is not 62.4 because 62.4 is U.S. units. We're dealing with SI, 9.81. And so when you chug that out, you plug and chug, you get kilonewtons per meter squared. Remember, kilonewtons per meter squared is a kilopascal. And so we get 221.7 Fail passes. That's an easy one, but I think it's important to understand effective stress because I think the problems, and not just this one, but the problems that I've done today, I'm not saying you're going to have problems exactly like them, and I don't think I would presume to make that prediction. But I think that the concepts that we're talking about here are very ripe for selection on the FE exam. And what we'll do next week is we'll sort of add to this by talking about some other, I don't say advanced topics, but some additional topics that maybe will somewhat fill the geotech picture up. I'm not, covering everything, but I'm covering enough that I think you can take an honest stab at this section of the exam. I want to make sure that I increase your bearing capacity for this section of the exam. I had to sneak in another one before we closed it out. Okay, any quick questions before we call it?
Michael said something in chat. I'm trying to get what it means.
It's a
Okay.
Bearing capacity. Basically, what he's saying is that I'm a dork, which is kind of true. I'll admit it. All right, everybody. Let's go ahead and call it. Everybody, I hope everybody has a great day. We'll see you all next week. I'm going to try and get this math review done as quick as I can because I know that we got to get that rocking and rolling. All right, everybody. We'll see you.